To the FPGA seminar, and so this is the first one of 2011. Happy New Year, everyone. So we have two papers today, and I believe this is a paper FPGA. Yep. So we'll let Andrew introduce what he's working on.
Okay. Thanks, Paul. Yeah. So as Paul said, my name is Andrew Canis, and I'm going to be presenting a short paper we got accepted at FPGA this year, and it's called LegUp, High-Level Synthesis for FPGA-based processor accelerator systems. So there's a number of people involved in this project. There's myself, Jong Sok and Mark, who are both master's students. We had two summer undergrad students who were helping us out, Victor and Ahmed. Our supervisors are Jason Anderson and Stephen Brown. And we also had some advice from Tom, who works at Altera. So let's just get into some motivation for what this topic is about. So hardware design can offer some compelling advantages over software. Especially if you have a parallel algorithm, you can get improved speed, improved energy efficiency. But the main problem is hardware design is pretty difficult. There's not a whole lot of people who know how to do it well. So the goal here is we need a better FPGA CAD flow that makes it easier for people coming from a software background to do hardware design. We'd like to make it a more of an incremental methodology. So the top level vision is the engineer will start with a C implementation of his algorithm. He'll push it through a standard C compiler targeting a soft MIPS processor, which is on the FPGA. And inside this MIPS processor is a profiler, hardware profiler, which will let the user run his code and determine what's taking up the most cycles, what's taking up the most power, any cache misses. Sort of profiling information that lets him decide, okay, this function would be a good candidate to move into hardware. Oh, so these program segments you push into what's called a high-level synthesis tool, which takes a high-level language like C and can produce synthesizable Verilog as output. And when you have the synthesizable Verilog, you can now put that into Cordis and compile what we call hardware accelerators, which are on the FPGA. And you get this sort of co-design system where some of your code's running on the soft processor, and then automatically the control passes into the FPGA to this hardware accelerator. When the accelerator is done, the control passes back. And this should all be transparent to the user. And ideally in the future, we'd also like this section to be automatic as well. You should automatically see, okay, this function looks like a good candidate and move it into hardware. Right now this is a manual process. You have to decide which parts of your program you want to move to hardware. And the nice thing also is the C compiler and this high-level synthesis framework is part of the same code base. I'll talk about that later. And these are just the people involved in the different parts of this project. So the key features that we're offering with LegUp is a high-level synthesis framework that can take in C and produce synthesizable Verilog. We're also going to provide some C benchmarks. So these are C code benchmarks that are sort of typical of the kind of code that you'd want to move into hardware where you could see some sort of advantage. We have a MIPS processor, a MIPS soft core, and this is from the University of Cambridge. It's called Tiger MIPS. And we also have a hardware profiler, which will let you determine how your program's running. And another very important part of this flow is these automated tests, which run functional simulations and model sim timing simulations to verify that your hardware actually works as you expect it to. And we'd like this all to be open source, freely downloadable, in the same way that VPR is for place and route or ABC is for synthesis. So the overall system architecture looks like this. As I mentioned, you have this MIPS soft processor on the FPGA. We've been targeting Cyclone 2, so Altera FPGAs. So that's connected to an Avalon bus. And you have a number of hardware accelerators which represent these hardened program segments, and they communicate to the processor through the Avalon bus. So what happens is sometimes you'll have global variables which need to be shared between the processor and these accelerators. So for that you need a shared memory controller which either accesses on-chip cache memory or off-chip SRAM. And I should also mention the hardware accelerators themselves have a lot of block RAMs for the local memory that's used by the hardware accelerator. So the high-level synthesis framework itself is built on an open source compiler infrastructure called LLVM, and this is actively maintained by Apple. It has a vibrant developer community. I was just at the dev meeting last month, over 200 people. It's a great piece, great infrastructure, well designed. And we want to support quite a large subset of C. So we want to support when we move to hardware. So we want to support moving functions to hardware, arrays, structs, pointers, globals. Some of the parts of C which we don't plan to support anytime soon are recursion So it doesn't really make sense to map a recursive algorithm into hardware. Same with dynamic memory. And floating point operations we just haven't implemented yet, but you could implement it in the future. So ideally, this high-level synthesis framework should be structured similar to LLVM, which is structured as a series of compiler passes, so optimization passes. So high-level synthesis is generally broken down into a few different stages of operation. So you have some user constraints, so timing constraints, area constraints, what type of FPGA you're using. And then you have an allocation stage which maps out roughly how your circuit architecture is going to look. You have a scheduling pass which determines for each operation which state, which cycle do I actually want to perform that operation, build up a finite state machine. You have a binding pass which shares any resources, and you have a pass that actually generates the RTL Verilog. So ideally this should be flexible so you can swap in and out the binding pass or the scheduling pass. We've had some feedback from Tom that the code isn't quite clean and modular yet, so I'm still working on this. It's a work in progress. So far what we've built up is a simple scheduler. So it's called as soon as possible. So each operation is scheduled in the state right after all its dependents all of its dependent operations are available. And our scheduler also supports operator chaining. So for instance, if you have a clock period that has some space to spare, you could have a few dependent adds within the same cycle. And we also support MultiCycle Operations, which you need for, let's say, a divider. You can't have a divider happening in one cycle. You need to pipeline that over many cycles. In terms of resource sharing, our binding algorithm is a heuristic called weighted bipartite matching. And generally in FPGAs, muxes are expensive, so you generally don't want to share an adder using a mux, so roughly the same area. But we do share the bigger units like dividers, multipliers. And we haven't focused at all on register sharing because FPGAs are pretty register rich. In terms of the C benchmarks that we provide, most of these are from a paper that was published September 2009, and they're called the CHStone benchmark suite. And I've listed the sort of applications that we have here. They're sort of typical of the high-level synthesis domain. So we have some software-emulated 64-bit double precision operations, some encryption applications, JPEG decoder. We also added DryStone because it's just a typical CPU benchmark. And the great thing about these benchmarks is they have golden input and output test vectors. So one of the most important things in high-level synthesis is you have this C code, you've mapped it to hardware. You want to verify that the hardware matches the software. So this is a crucial thing to have. It's almost like a built-in self-test. And as far as I know, no other academic tools could actually support the CHStone benchmark suite, because they use quite a lot of C syntax and C semantics that the previous academic tools didn't support. So now to get into some experimental results. There were 5 data points that we looked at. So first we took the benchmarks and compiled them purely into software to run on the soft MIPS core. Next we have 2 hybrid points. So the first hybrid, we took the second most compute-intensive function and all of its descendants, and we mapped that into hardware. We also took the most compute-intensive function and all its descendants, and we mapped that to hardware. And then we have a point where, first of all, we used LegUp, and we took the C program, pushed it entirely into hardware. And we did the same thing for Excite, which is a commercial high-level synthesis tool. And the resulting graph looks like this. So the 5 points I just mentioned are shown on the horizontal axis here. So on the far left, we start with a pure software implementation of the benchmarks. And the execution time is shown by this dark line right here. So as you can see, as you push more and more of your program into hardware, the geo-mean execution time decreases for the benchmarks. The blue bar graph in the background shows the number of LEs required for each one of these data points. So when you're putting everything into software, all you need is the MIPS core. Is that serious?
Just watch the cord.
Sorry. When you put everything into the MIPS core, all you need is just that soft MIPS core. As you push more and more of the program into hardware, your area needs to increase because now you have these hardened segments of the program. But then when you go from these hybrid solutions to a pure hardware implementation, you no longer need the MIPS core. So the area, that's why the area drops in this case. And the execution time for the pure hardware solution is about 8 times faster than pure software. On average, like geo-mean average over the benchmarks. And another interesting graph to look at is the energy consumption consumed by the benchmarks. And we got this by just doing a full timing post-routed simulation and running it through Quartus power analysis. And as you can see, as you go from software to a full hardware, your energy drops dramatically. In the extreme case where you're in pure hardware, you get about 18x less energy than a software implementation. So the energy results are pretty compelling. So one of the questions you'd like to ask is, how does our high-level synthesis tool compare to a commercial tool? So the only commercial tool we could get our hands on was a tool called Excite. It can't compile DryStone, so we just ignored that benchmark, but it supports the whole CHStone benchmark suite. And what we found was, so we took the C programs, compiled them entirely into hardware, and our circuit runtime was about 20% faster than Excite, but our logic elements were about 20% higher. So if you look at sort of an area delay product metric, we were roughly on par with Excite. So what does this tell us? I mean, it tells us we're, not in the same general ballpark as a commercial tool, so it's a somewhat decent baseline to start off with. So we will make improvements from here. So just to dig into those numbers a little bit more. So I've shown here the number of cycles it took LegUp to complete the benchmarks, each one of the 12 benchmarks, and the number of cycles it took Excite to complete each one of the benchmarks. And what you can see is that generally LegUp took a lot more cycles to complete each benchmark. In the extreme example, for DFAD, we took 6 times the number of cycles to complete that particular benchmark. But when you look at the Fmax results, our Fmax is generally higher than Excite, which means we pipelined our units a lot deeper. We didn't try to pack as much into a single cycle. So like for that same example of 6 times the number of cycles, our Fmax was 5 times higher. So when you take cycles and multiply it by 1 over the Fmax, you get the runtime for each benchmark, and that's shown right here. So we ended up 20% faster than Excite overall. And that's also shown graphically. So this is the ratio of LegUp circuit runtime over Excite runtime. If we're left of this black line, we're faster. If we're right, we're slower. So there's a couple outliers here. For instance, AES, we're about 5 times faster. But motion, we're 2 times slower. This probably has to do with the pipelining we did versus Excite. Another very useful comparison to make is comparing a pure hardware implementation to a pure software implementation to see sort of how much room's on the table for improvement. And when we compare these two, we see that a pure hardware implementation using LegUp gets about an 8x better circuit runtime than a pure software implementation. And that costs us, so if we compare the MIPS core to these hardware solutions, we're about 30% more LEs, and roughly the same multipliers, less memory bits because we don't need a huge cache anymore. So we get a lot better runtime by moving completely to hardware. And if we break that down into each benchmark, we can see for a couple, especially the 64-bit emulated benchmarks, you can get quite a big speed up. So let's say for double precision sine, we get a 35x speed up. So there are some cases where you get a huge speed up, just depends on the benchmark you're looking at. So just ongoing work in this project. We're looking into the overall system architecture. So the memory hierarchy, we're looking into maybe having multiple clock domains for each hardware accelerator. There's lots more work to do in the high-level synthesis portion. I really need to implement modulo scheduling for loop pipelining. I don't have any loop pipelining right now. I really need to refactor the code before this paper gets published based on the feedback I've got. And it would also be nice to do some more hardware profiling and make it so it's more automatic, so portions of your program automatically move to hardware. And yeah, that's everything. Okay, thanks.
Questions? Yeah, you got it.
So you're comparing to the MIPS processor, right?
Yeah.
Is it Tiger MIPS?
Yeah.
So, I mean, did you show just the properties of the processor alone, like Fmax?
The Fmax of the processor is 75 megahertz.
75 megahertz, right.
It's a 5-stage processor. It's slower than ES.
Yeah. Do you know like the average like IPC? What would be the IPC across this, let's say this benchmark set, right?
I don't know that off the top of my head, sorry.
Right, because the IPC, like for example, like Neos is also like 5-stage, right?
Yeah.
And they say like the IPC would usually be like around 1 in most cases, right? When you have like a huge data cache and huge instruction cache, so you take that out of the equation, right?
Yes.
So then they say that would be like IPC 1, right? So pretty much if you're running it like 300 megahertz, right? That's pretty much, that's what you get, those 300 MIPS, right?
Yeah.
Million instructions per second, right?
Yeah.
Because IPC is around 1. So I just wanted like back of envelope comparison of this Tiger MIPS, right?
Yeah.
Like let's say, assuming that IPC is 1, which would probably need dynamic branch prediction and like instruction cache and data cache, right?
It does have an instruction cache, data cache, and it does have branch prediction.
Okay, so yeah, so you could
But
assume that
it's
IPC is
slower than Neos for sure. Like maybe 2x slower at least.
Yeah, so Neos can run easily 290, right?
Yeah.
This is all Cyclone 2. This is all Cyclone 2.
Yeah, it's Cyclone 2 too.
Okay,
This
so
isn't Stratix.
so what's the Cyclone 2 then?
It's around 2x based on Altera data sheets and stuff when we looked into it.
In terms of Fmax, right?
Yeah.
Yeah, but we heard anecdotally from Altera that some MIPS implementations on Altera, soft MIP implementations on Altera were slower than the Neos, we heard anecdotally. So it wasn't, the numbers for Tiger MIPS were not out of whack with other MIPS implementations on Cyclone 2.
Yeah. I'm just saying that it's nice to compare to the best soft processor that you have out there, right?
Yeah.
What you're saying, right? Because you could get this, like you can run all of this on Neos as well, right? Like just the pure software version, just to show what's the benefit over actually running it on the, because I have an option of using the best soft processor that there is, right?
Yeah.
Right? Or high-level synthesis, right? So if high-level synthesis beats the best available, like.
But I think you got the answer to your question, which was 2x, right? They measured up against their
Yeah.
processor up against Neos.
So let's say, yeah.
No, I'm just saying it would be nice to compare, right? I agree, right?
Yeah,
I would just
yeah.
put, put MIPS, I would put all of them, right?
Yeah.
So
I mean,
just
it was
show-
only like, it's only a short paper, so we just didn't have room for that. I mean, because there's a lot of other data we had in there, like all the area results, all like the time results. We just didn't have enough space for it.
Yeah.
But
I
yeah,
understand.
we did look into that. Yeah.
I was just wondering about kind of the overall runtime of the not the execution runtime of the circuit, but of the CAD flow.
Of the CAD flow? Oh, it's on the order of like seconds.
Really? It's like really...
It's really fast. Well, if you don't include the Quartus, like the Quartus side, right?
Just
Like
the
taking
high-level
C
part.
code and converting it to Verilog. For our implementation, it's really fast. Excite was slower. Like Excite for some of the larger benchmarks took like a day to run. But it's probably because they had some NP hard algorithms which they just hadn't optimized that well. All our algorithms are like polynomial time. They complete really fast. So, yeah.
Okay, another question about your tool versus Excite. You answered the first one about compile time. It's about register usage. So you say that your tool tends to pipeline more than Excite.
Yeah.
Do you know how much register usage it has compared to Excite? And also, does it really matter because the LE count includes registers, right?
Yeah.
Okay. So it doesn't really matter the fact that you might use
We
more
do use
registers.
more registers for sure. A lot
But-
more registers.
But can you also say that it doesn't matter that you use more registers
Yeah.
given the area numbers you have?
Yeah, exactly. Exactly.
There's a register for each lot too, so it's kind of bit free.
Yeah. Yeah, so we didn't focus. I think they focused a little bit more on sharing registers. But the problem is when you share registers, you now have a mux in your clock period, so I mean, it's not really worth it in my opinion, at least at this stage.
So could you claim maybe that your approach is smarter for targeting FPGAs because of the register abundance than their approach of conserving registers and trying to cram as much as possible into one cycle?
Yeah, you could probably say that. Probably need to run some more experiments to verify that, but yeah.
Ooh, another question. Are you interested in using a D or the D4 in our room for a better for a better platform?
Yeah, we just actually got 2 DE4s in, so we're gonna work on that. Yeah. But right now it's just Cyclone 2. Yeah. Great.
Could you maybe walk us through what your envisioned use scenario of this would be? Meaning, if I'm building a system, would I do this profiling and adding accelerator stuff? Would I kind of do that offline and then ship my product once it's all done? Or do you envision this kind of happening on the fly in a live system that's out in the field?
Yeah, I mean, the long term, it would be nice if it was working in the field automatically, you know, just in time working. The problem is you need access, with this flow, you need access to the original source code to actually create the hardware. So an interesting like related project is called the work processor, which was done at UC Riverside. So they actually have the binary that's been compiled, and then they basically disassemble the binary and just in time create these hardware pieces which speed up the code. So I think this is a level a little bit above that. I don't think it would quite be just in time. But hopefully it should be automatic, so you could have some piece of code running, and if you have access to the source, you could slowly be profiling and automatically deciding which portion of the program would go to hardware. So, yeah.
Two questions. First one is, so your part of the CAD process is pretty quick, but then the resulting hardware descriptions, how long would that take to go through ports? So what's the total CAD time of this?
Can't think off the top of my head. It's probably
Typical.
a couple hours for sure.
Couple hours. That's to do all the benchmarks or each
Yeah.
one?
Not to do each one. No,
Okay.
to do all the benchmarks. A couple hours for sure.
All right.
Especially if it's been like, if it's just incremental compilation.
Yeah.
It probably takes like 2 hours for most of them, for doing most of them all together, and then for JPEG, that one takes a little bit longer, maybe an hour just for itself.
All right. And then the other one is, so your final results compare well with Excite. Now, do you have an idea of how these results compare to, say, handmade native Verilog implementations?
That I don't know.
Okay.
That would be very interesting.
I wonder what's the boundary between your generated stuff
Yeah,
and
yeah, I'd really like to know
stuff.
that too. I have a feeling it's quite far off because the hardware we generate is fairly naive in that we just have the state machine and everything's fairly sequential. We mainly take advantage of instruction level parallelism. Like I mentioned, there's no loop pipelining. So if you actually, when you're actually developing hardware, you're pipelining things a lot more, you're duplicating a lot more. I think if you did it by hand, it would be a lot faster. But I mean, that's just the whole research, like extracting some of this parallelism and doing that, some of that automatically is just part of the research here.
Okay.
Yeah.
That just makes me want to ask the question, how would your whole goals change, or these results change if you had a hard processor doing this?
A hard process.
So
Comparing it against a hard processor.
Yeah, imagine a world in which an FPGA had a fast hard processor on it. Do you consider that future in any of this thinking?
Yeah, I mean, it would be a very similar system, right? You would have this hard processor now, and probably would be faster, so maybe you'd have to be a little bit more concerned about what you're putting into hardware, but the whole system would work very similar. And that is like the end level.
Sure, but fast hard processor is going to be, I don't know, say 10x at least faster than that soft processor, right?
Yeah.
So that means your gains are going to have to be that much.
Yeah. So I mean, this is just a baseline to work on. Like, part of the reason I wanted to work in high-level synthesis is because I think there's a lot of potential for improvement. There's a lot of potential for getting more parallelism out of these automatically generated designs. So you probably maybe even want to use like a CUDA-like framework or some like higher level, even than C, to actually extract some more of that user parallelism and generate more actual hardware units. It's probably what you want to do. Yep.
I was just kind of thinking of, I didn't really see the size of programs that you were actually putting into hardware. Like you see the pure LegUp hardware design is roughly about the same size as the MIPS, but that's based on the size of programs you're running. Like how big a program can you have? Because as your program gets bigger, I assume your hardware also has to get bigger to put it all into the hardware, right?
Yeah. So what do you, like, how big are the C programs, or how big?
Yeah, how big are the C programs do you use, and like what sort of like kind of limit on size of C programs you think you can actually put into hardware?
Yeah, so the biggest benchmark that we looked at was JPEG, which was 1,700 lines of C. And that produced, if we go back, it's probably there, but something that I think when you ran a physical synthesis, I don't actually have the results here. When you ran physical synthesis, I don't think it could fit on a DE2, Cyclone 2. So it was fairly big. In terms of like the limit of what you want to do, I mean, it's hard to answer that. If you scaled up to like a Stratix 4, you could start putting some pretty big programs in. But I don't think you could put like, you couldn't put like a 1,000,000 line C program through this flow probably. Just because to support all that C syntax, you'd have recursive algorithms, you'd have things that,
Right, so you're saying that JPEG wouldn't fit on the Cyclone 2, so like if you wanted to do MPEG, right, you actually had video, then
yeah,
you definitely have to go to like a Stratix.
you've got to go to Stratix, yeah.
We also don't have resource sharing yet, right? So,
Resource sharing, we have resource sharing for dividers.
but yeah, it's very basic, right? So you can
Yeah.
probably
Yeah, we can
squeeze a
share.
lot more.
Exactly, yeah. Yeah, right now we don't, a lot of the pipe, there's not that much sharing, like it's a sort of sequential hardware. We got to share more hardware, especially for like the DSPs. Usually, so what was happening with Cyclone 2 was like the DSPs were limiting us. So by sharing more multipliers a little bit smarter, you can probably reduce the DSPs if you see you're coming close to device maximum. Yeah.
So one question for you.
Yeah.
So your fundamental premise was that this makes it easier for people to program FPGAs, right? They start
Yeah.
off with C. So at the end of the day, let's say you make this as efficient as you possibly can,
Yeah.
right? So C is the entry flow for an FPGA. Is it going to be as efficient as running that C code on some other processor or a processor-like thing?
I think it would be more efficient, right? Because you can just get way more parallel.
But can you?
If you can extract it out of the C, right?
Has anyone ever done that?
I mean, there's work in loop pipelining, right? So
Yeah.
you can look to that. Yeah.
There's also the energy arguments too, right? Versus a processor. That's going to be one of the motivations for pushing computation into hardware too, not
Yeah.
just runtime.
Yeah, but you also don't have to compare yourself to an x86, right? You can compare yourself to a low-power ARM processor as well.
True, yeah.
Yeah, I mean, that's the real question. I mean, probably actually the real question is, let's say I have like a system spec that I need to meet. Can I get hardware that's good enough to meet that spec, right? Like, let's say if I have a constraint where I can't put like an x86 processor, like I need some embedded processor which isn't superscalar, can't extract like as much parallelism. Like, can I meet my constraint in a much faster time using this method than, let's say, like just sitting down and doing hand RTL? Or maybe you could explore the architecture a lot faster using this, and then actually end up getting a better RTL design than you would without it. So, yeah, I mean, it's hard to compare to like a standard x86 because it's really almost like different domains. But yeah, you're right. It's a tough problem. Yeah.
So you said JPEG is 1700 lines of code.
Yeah.
So do you have how much of that do you actually compile to hardware of those 1700?
All of it.
All of it?
Yeah, that doesn't include comment lines or.
So why all of it?
It was just to show like what would happen if you compiled the whole thing.
Okay.